Hello everyone and welcome to another lesson. Professor Mab here. The topic of today's lesson is design procedure for multi-axial static loading. Design procedure for multi-axial static loading consists of 4 steps. First, calculate the maximum stress caused by each of the following loads: axial, bending, torsion, and shear loads. In step 2, we need to add similar stresses together to determine the resultant normal and shear stress components. Step 3, we'll find the maximum stress state by calculating principal normal and shear stresses. And finally, in step 4, we need to use a design failure theory that is suitable for our application to calculate the factor of safety or determine the material's strength based on what information is given. An axial force results in a normal stress. The assumption of a uniform distribution of a stress is commonly made in design applications. The normal stress, sigma, is defined as the ratio of the axial force over the cross-section area. The tensile normal stress is considered positive, while the compressive is negative. The second type of loading is bending moment that results in normal stress. Consider a bar subjected to pure bending. All elements of the bar on XZ plane, which is the neutral plane, have 0 stress. The bending stress varies linearly with the distance from the neutral axis, y, and is given by my over I. In this figure, the normal stress above the neutral axis is compressive, negative, and below that is tensile, positive. I is the second area moment about the z-axis. It can be found for various shapes from design tables. For example, I for a circle is pi d4 over 64. The maximum bending stress will occur where y is the largest, which would be at the outer perimeter of a section. For shafts with solid circular cross-section, using y maximum as d over 2, the maximum bending stress can be calculated as the following. The third type of loading is torsion, caused by a torque vector tending to twist the element. As the result of torque, shear stresses develop throughout the cross-section. For a round shaft in torsion, these stresses are proportional to the radius and are given by T rho over J. J is polar second moment of area and can be found from design tables. For circles, J is pi d4 over 32. The maximum torsional stress will occur where radius is the largest, which would be at the outer perimeter. For circular shafts, using maximum radius as d over 2, the maximum torsional stress is given by the following equation. A shear force results in a shear stress. There are 2 different scenarios when analyzing the shear force. First is the direct shear that occurs when there is a shearing action with no bending. This results in a shear stress. Tau equals V over A. This shear stress is uniform on the entire section. The second type is when shearing is accompanied with bending. In this case, the shear stress, also called the transverse shear stress, is calculated by V Q over I B. Detailed analysis of this equation is explained in a different video. For design purposes, we'll only need to determine the maximum stress. The distributions of transverse shear stresses for a few commonly used cross-sections are shown in this figure. For most sections, the transverse shear stress is 0 on the perimeter and maximum on the neutral axis. This is exactly the opposite of where the bending and torsional stresses have their maximum and 0 values. Therefore, transverse shear stress is often not critical from a design perspective. Having discussed these 4 different load types, step 1 is complete. Step 2 consists of adding similar stresses together to determine the resultant normal and shear stress components. Remember, stress is a vector and its direction needs to be determined in any loading case. In step 3, we'll find the maximum stress state by calculating principal normal and shear stresses. This was discussed in another video in this channel, whose link is up here. And finally, in step 4, we need to use a design failure theory that is suitable for our application. We will calculate the factor of safety if the material's strength is known, or will determine the material's strength if the design factor is prescribed. Several important design failure theories were discussed in another video that is linked on the top right of the screen. Thanks for watching this video. Please let me know your questions in the comments section.